Sometimes a function is defined using two equations on different parts of its domain. An example is an absolute value function, which is f of x equal to absolute value of x. And this is defined by two equations. So y is equal to x when x is greater than or equal to 0, and y is equal to a minus x when x is a less than or equal to 0. So let us define the following functions below. So if we define absolute value of x minus 3, the x value where x minus 3 is 0 is at x equal to 3. So its graph has its vertex at x equal to 3. So if we define this function following this definition of absolute value of x, so we replace x minus 3 for every x in the given function. So this is defined by the first equation, which is equal to x minus 3, where x minus 3 is greater or equal to 0, following this definition. And then the other one is the negative of x minus 3, where x minus 3 is less than 0. So if we will solve this inequality here, the first equation will be x minus 3 if x is greater or equal to 3, and the other one is negative x plus 3, where x is less than 3. So as you can see here, the 0 or the critical value of this x minus 3 is x equal to 3. So that is the boundary here. For another function, which is absolute value of 4 minus 2x, the x value where this 4 minus 2x is 0 is at x equal to 2. And look at its graph. Its vertex is at x equal to 2. So let us define again the definition of this absolute value, which is two equations. The first equation is 4 minus 2x when 4 minus 2x is greater than or equal to 0. And the other one is negative of 4 minus 2x when this 4 minus 2x is less than 0. So if we will solve this inequality, so we will move the positive 4 on the other side, so it will give us negative 4. And then dividing both sides with a negative number in an inequality should reverse the inequality symbol. So x is less than or equal to 2. And the other one will be x greater than 2. So if we will simplify, so this is equal to, the first equation is 4 minus 2x, where x is less than or equal to 2. And then the other one is negative 4, distributing negative 4 plus 2x, where x is greater than 2. So if you can see here, the 0 of this graph or the 0 of this function is x at equal to 2. So that is the boundary on this two equation. Now if we will have a general observation in the absolute value function, in this absolute value of x minus 3, where coefficient of x is a positive, so for the first equation is a positive x minus 3, means this positive x will go with a greater than or equal to in its domain, and with negative x will go with the less than. Look at the absolute value of 4 minus 2x. In 4 minus 2x, the coefficient of x is a negative 2. So this 4 minus 2x with a negative 2 as coefficient of x will go with a domain with less than or equal to instead of greater than. And the second equation is negative 4 plus 2x. This is plus 2x, meaning it will go with a greater than in its domain. Now, if I will write the absolute value function in a shortcut way, so if I will define the absolute value of 2x minus 8, first I will define first the 0 for this. The x value that makes 2x minus 8 0 is equal to 4. So that's why the boundary here is a 4. Now, the first equation is 2x minus 8. Since I know that the coefficient of x here is a positive 2, this will go with domain with greater than or equal to. On the second equation with coefficient of x as a negative 2, then it will go with a less than in its domain. And then if I have absolute value of 5 minus x, again, I have to find the 0 here. The x value that makes the 0 is 5. So meaning this is the boundary value here, which is 5. And then the first equation is 5 minus x. And since this x goes with a negative number, and then here it will go with a domain which is less than or equal to. And then since the second equation is negative 5 plus x, and x is coefficient is positive 1, then it will go with a greater than in its domain. So you can try. This is an example of piecewise defined function. So in this example, we will analyze the function f with three given equations and different domains. So in determining the domain of the function, this is the union of this domain in each function. So let's find the domain of f. So first, the given interval in the domain is from -1 up to 2. So we can put that in a real number line. So -1 up to 2, -1 and 2 are not included. And then on the second equation, the domain is x equal to 2. So we will shade the value of x, which is equal to 2. And then for the third domain is x greater than 2. So from 2 to infinity. So we will shade from 2 to infinity. So we can see here that the domain of the function f is from -1 up to infinity. Now let us discuss first letter C before letter B, finding the y-intercept of the given function. In finding for the y-intercept, we have to set x equal to 0. So first, since x is the domain and we have different domains, so you have to select where is x equal to 0. X equal to 0 is in the first domain and the equation is 1 minus x squared. So you will use this function with the first equation. So you will substitute 0 for every x in the given function on the first equation. So it will give us 1 minus 0 squared, which is equal to 1. So the y-intercept is 1, or you can say that y-intercept is 1 or the point 0, 1. The next question is finding the x-intercepts algebraically, if any. So in finding for the x-intercept, we have to set y or f of x equal to 0. Since function has three equations, so we have to equate each equation to 0 and find the value of x and check if it's in the domain. So in the first equation, we have 1 minus x squared equal to 0, and then moving negative x squared on the other side, so we will have x squared is equal to 1. And then getting square root of both sides, we will get the two x values, which are positive and -1. So in this positive and -1, so these are supposedly the x-intercepts comes from the first equation. But in this first equation, the given domain is only from -1 up to 2. So here, this one is included in this domain, so we can say we accept this as x-intercept. But -1 is never included in this domain of the first equation, so we have to reject this -1. So the only x-intercept on the first equation is x equal to 1. Now let's move to the second equation. The second equation is 1 and we have to equate it to 0. Since 1 can never be equal to 0, so we cannot find any x-intercept here. And then let's move to the third equation. In the third equation, we have square root of x minus 2 is equal to 0. And then moving minus 2 on the other side, we will get square root of x minus 2 is equal to 2. And then getting rid of the square root, we have to square both sides. So x minus 2 is equal to 4. And then moving -2 on the other side, so x is equal to 6. Now this x equal to 6 is supposedly the domain for, or the x-intercept for the third equation. And in this third equation, the domain is x greater than 2. Since we know that 6 is greater than 2, so meaning we have to accept that 6 is the x-intercept for the third equation. So therefore, the x-intercepts of the function f are 1 and 6, or points 1, 0 and 6, 0. And take note, in finding for the x-intercept, it is required to show that you have to equate to 0 in each equation. So since we have three equations, make sure that you equate these three equations to 0 and you have to show your solution. Now let us graph this function f. On the first equation, this is the graph of a parabola that opens down. It is opening down because the coefficient of x squared is a negative. While the second equation, when x is equal to 2, y is 1, this is a graph of a point. While on the third equation is a square function, meaning this is a curve. So let us start graphing the parabola. So in this parabola, since the domain is from -1 up to 2, so we will start at the endpoints -1 and 2. Even -1 and 2 are not included. So we will just make it as an open points since these are the boundary points. So when x is equal to -1, just place -1 in x. and then find the y, which is 0. And then another is the endpoint is 2, substitute 2 in x, and get the value of y. So this negative 1, 0 is an open point because negative 1 is not included. And then this 2, negative 3 is also an open point because 2 is not included. And then here we have to connect these points using a parabola, meaning a curve, but these 2 points are not enough. So let us try to find another point in between negative 1 to 2, which is 0. So when x is 0, we know that's the y-intercept. And if you can recall, the y-intercept on the previous slide is 1, so it's 0, 1. So when x is 0, so try again to put 0 in x, so you will get the y value, which is equal to 1. So we have a point 1, 0. And another one is we already solved the x-intercept on the previous slide, which is 1, 0 and 6, 0. So from here, you can see that the parabola should always have a symmetry, and the symmetry is this y-axis. Meaning, if negative 1, 0 is a point, 1, 0 is another point. So you can connect this curve passing at this 1, 0. So this is the graph of the parabola. Then, for the second equation, we have a point which is 2, 1. So we'll just consider putting a point 2, 1 on the graph. Then, on the given curve, which is square root of x minus 2, so we will start when x is equal to 2. And when x is equal to 2, so we will substitute 2 in the value of x, so we will get the value of y, which is equal to minus 2. And then after 2 is, you can substitute 3, 4, 5, 6, and so on. But here, it's better if you will substitute 6 in the value of x, because if x is equal to 6, this square root of x minus 2 will give us square root of 6 minus 2, which is square root of 4. It is an integer or a whole number. So we have square root of 4 minus 2, which is 2 minus 2. It will give us 0 if we will substitute 6 in x. So it will give us 0. So here we have an open point at 2 because 2 is not included, and 6 is included because it's greater than 2, so we have a close point. Now connecting this curve not as a line, but connect this using a curve. So that's the graph of the function f. Now in this graph, we can find letter E, which is we have to use the graph of f to find the range of the function f. And in finding the range of the function f, we have to look at the vertical part. So on this vertical part, the graph is started below from negative 3 up to infinity. It is infinity because this curve will increase up to infinity or unbounded. So we have the range which is from negative 3 up to infinity, but negative 3 is not included because the y here at negative 3 is an open point. Now for the next question is f continuous on its domain? If not, determine the x value of discontinuity. So the domain is from negative 1 up to positive 6. So we cannot say that negative 1 is discontinuous because this is not included in the domain. So we can consider that it is discontinuous at x equal to 2 because you can see a jump at x equal to 2. So we have the answer here, which is no, and f is discontinuity at x equal to 2. Now, if we will recall what we got on the previous slide, we have to recall that the x-intercepts are 1, 0, and 6, 0. So you can verify these values that you solve algebraically in the previous slide and verify that in the graph. So we can see here that 1, 0 is x-intercept, which is correct, and 6, 0 is also x-intercept. And then the y-intercept is 0, 1, 0, 1, which is here. So this x-intercepts and y-intercept is correct in your graph. So this is correct. Now the next example is about the spot the error. So for the first given, we will write a definition for the graph of the piecewise defined function f. And this is Abdullah's answer. And from his answer, there are 4 number of errors. So let us start with this graph on the left side. So this graph, it looks like this is not y equal to x because this is the graph of y equal to x. But if we will reflect this across the y-axis, this is the graph of y equal to negative x. So it means to say, this graph on this part this is the graph of y equal to negative x. So it means in Abdullah's answer, this x is not correct. So if we will correct this, so we will change the y or f of x equal to minus x instead of x. And then if you will check the domain, it says that x is less than 0. When you say x less than 0, starting from 0 and then to the left side, this graph should be with arrow on this part. But since there's no arrow, there's a stop endpoint here. So we can say that x is from negative 2 up to 0. So this is another mistake. So let's encircle that. And to correct that, so we will write that x is between negative 3 to 0, including negative 3, but not including 0, because at negative 3, there's a closed point, and at 0, there's an open point. So we're done with the first graph or the first equation. For the second equation, so let's consider this point. And this point is when x equal to 0, y is equal to 2. So it looks like this part is correct. And for the last graph on the right side, so Abdullah's answer is x squared. And we know that x squared is a parabola. And if we will graph a parabola, the graph will be like that. So it looks like this is the third error, which is x squared. And let us discover what is the graph. So you can see that when x is equal to 1, y is 1. When x is equal to 4, y is 2. It means to say you're getting a square root of this number. So we can correct this function as equal to square root of x. Now, looking at its domain, it says here that x is greater than 0. But here, the graph will stop up to this. So it's not up to infinity. So it means to say this is the fourth error. And to correct that, the domain is only from 0 up to 4, not including the 0 and 4. So this is the correct function. Now for the last example of spot the error, let us rewrite this function as a piecewise defined function. And this is Ali's solution with 3 number of errors. Now if we will recall in the function with absolute value, we have to define this into equations. And with Ali's solution, it looks like the first error is in this part. Because when you define this absolute value, you do not need to write the absolute value anymore. So let us identify that this is the first error. And to correct this, we just change the absolute value to a parenthesis and creating the same 2 equations. And then after that, let us look at the domain of the first equation. If we have an absolute value with 1 minus x, so we need to identify the value of x here that makes 1 minus x 0, and that value is x equal to 1. So it looks like the boundary here is not correct. So this should be 1. And we will also check if the inequality is correct. So this is the second error. So if you will correct this, since the absolute value is 1 minus x, we will substitute the 1 minus x here. So 1 minus x should be greater than or equal to 0. So that is the mistake here. And then solving for x here, we move 1 on the other side. And then dividing both sides with negative, since we divide both sides with negative number, we have to reverse the inequality symbol. So we will get x less than or equal to 1. So this is the domain of the first equation. Now for the second domain on the second equation, so we can identify that this is also a mistake. Because if the boundary is 1, when this is x less than or equal to 1, so in the other equation, it should be the opposite of this, which is x greater than 1. And now, to complete this, we just need to simplify that. And simplifying the first equation, we will get the same value, which is negative 2x plus 1, where the domain is less than or equal to 1. And another equation is, simplifying this, we will get 2x minus 3 when x is greater than 1. So if you will notice here, when we have an absolute value in 1 minus x, and x is a negative number, so the first equation will always give you with a less than or equal to, not a greater than. That's all. That is the end of this video. If you find this video useful, please like and subscribe and turn on the notification bell so you never miss out on the future content.